Hey physics champs, Tanya Chew here. In this video, we are cracking open IGCSE Physics May-June 2025, paper 62. If you're tired of losing marks in the written practical because of the errors, this video is going to save you. I'll show you how to write your answer like a top scorer and explain every tricky part clearly. Ready? Let's dive straight and beat this paper. Now, let us begin with the first question first. A student determines the internal diameter D of a test tube. Apparatus is assembled as shown in Fig 1.1. A. The student fills a measuring cylinder with water up to 100 cm cube mark and pour some water from the measuring cylinder into the test tube. First part, a full-size diagram of the bottom part of the test tube is shown in Fig 1.2. On Fig 1.2, measure the height h in centimeters to the nearest millimeter. Record your result in the top row of Table 1.1 on page 4. Now, before you do your measurement, I would strongly advise you to print out this past year paper. Whenever you want to print out any paper 6 past year paper, make sure that you remember to set the setting on your printer, right? Print it in actual size so that your measurement will be almost similar to the mark schemes. Right, page 4. Where is my page 4? So you just use a ruler to measure the h. The h that I measured was 3.4 cm. So 3.4 is the answer. And okay, now go back to the next page. The second part, Fig 1.3, shows the volume of water remaining in the measuring cylinder. Take the reading R of the volume of water remaining in the measuring cylinder. Record your result in the top row of table 1.1. This is reading R. Remember, this is reading R. Right, so this volume is reading R. So before you take your reading, when a diagram is being given, when a figure is being given, make sure that you take the reading below the meniscus. So this is actually 89 cm cube. So I'm going to fill in the table. R is 89 cm cube. And the third part, calculate the volume V of water poured into the test tube. Use the equation V is equal to 100 cm cube minus R and record your result in table 1.1. So I'm going to calculate V. V is equal to 100 cm cube minus R, 89 cm cube. And I got 11 cm cube, and I'm going to record that in table 1.1. So this is 11, and we are done with the table. Part B, the student adds more water from the measuring cylinder into the test tube, measures the new height h of the water in the test tube, measures the new reading R of the water remaining in the measuring cylinder, calculates the volume of water V in the test tube, repeats the procedure for 3 more values of H, R, as well as V. So the student's results are shown in the table 1.1. It is important to avoid line of sight. We call it as parallax errors when reading the scale of the measuring cylinder. Describe how such errors are avoided. You may draw a diagram. When the question mentioned that you may draw a diagram, I always draw a diagram. So whenever, okay, this is my diagram of the measuring cylinder. Okay, I just draw it. And then this is, could you see that? This is a curved line. This curved line is called meniscus. So you got to make sure that your eye position, to avoid parallax error, your eye position of your eye is perpendicular to the scale. Scale is here, horizontal. And your eye position is 90 degrees from the scale. This is called 90. Right, could you see that? So I would say that this is a measuring cylinder. Measuring Whenever I draw the diagram, I will label the diagram. And this is a water. And this is my eye. And this is called meniscus. Okay, I'm going to use different color. Right, this is called meniscus. So the explanation, I would describe it. Okay, make sure to take reading below meniscus. And okay, also make sure eye position is perpendicular to the scale on measuring cylinder. We are done. Now the next one. C, plot a graph of V/CMQ on a y-axis against HCM on your x-axis, and you have to start your axis at the origin, 0, 0. And you have to draw the best fit line. The 0, 0 is here. So what you do now is that I'm going to label this first, VCMQ. That is my y-axis. And this is H in CM. That is my x-axis. Now, I need to know that this is my x-axis. X, this is my y-axis. I look at y first. Y, the smallest is 11 and the largest is 47. 11, 47. Okay, I am going to start with 10. 10, 20, 30, 40, and 50. That's my scale for the volume, y-axis. And my x-axis, the smallest is 3.4 and the largest is 13.6. I might want to start with maybe smallest is 3.4. So I'm going to start with 2, 4, 6, 8, 10, 12, and 14. I'm done. And then now we're going to plot that points, all the readings here. When x-axis is 3.4, y-axis is 11. Where is my 3.4? I'm going to use a ruler. This is 3. 3.4 is here, and then my reading on my x-axis is 11. This is 10 divided by 10. So the scale, one small box represent 1. So this is 11 right here. I'm going to plot it. And then the second one, when H reading is 5, V reading is 16. 5 and 16. Where is the 5? This is 5. And then I need to have 16 right here. Okay, this is, here is 10, 11, 12, 13, 14, 15, and 16 is here. And then the next one, when the reading of H is 7.6, V is 25. 7.6. This is 7. 7.6 is here. And the Y reading is 25. 1, 2, 3, 4, 5 is here. So I'm going to plot that point. Okay, this is the point. And then after that, when the H reading is 10.3, the V reading is 36, 10.3. So this is 10.2, 10.3 is at the middle. Okay, and the V reading is, let me check again. The V reading is 36. 31, 32, 33, 34, 35, and 36 is here. I'm going to erase the dotted line later, so you don't have to worry about that. Okay, this is 10.3 somewhere here. Okay, this is the point. And then the last one, when H reading is 13.6, V reading is 47. 13.6. This is 13. This is 13.6. And I need to get a value of 47. Okay, I start from 50, 49, 48, and 47 is here. Okay, let me plot it first. Okay, this is the one. So I am going to erase the ugly dotted lines. Okay, when you draw on the paper, it is easier because you can just use your ruler. You can just use your ruler as an indicator of the readings. Here, these are all the reading unwanted dotted lines here. So I'm going to erase first. Here. Okay. Okay. So this is the X. And I am going to draw the best fit line. Okay. Now, let us see the best fit line. Okay. Okay, this is the one. The best fit line doesn't mean that, right? It has to pass through all the point. It is, okay, it means that make sure that all your readings, all your points must be closer to that straight line. Cannot be far deviated, right? So it doesn't, okay, it doesn't matter if not a single point on the straight line. It doesn't matter. So I'm going to draw that best fit line using this color. So this is the one. Okay, I'm going to extrapolate it and then I'm going to keep the ruler first. Okay, this is my best fit line. Could you see that most of the points are not exactly on the straight line, but all the points are very close to the straight line. All right, so I'm done with that. And then D, determine the gradient G of your line. Show all working and indicate on the graph the values you use. Okay, so we have to show that the values that we use on the graph. So I'm going to check which is the easiest point. It seems like this one. Okay, I'm going to take this point. So this is 1.4. This is 1.4 and 3. So you have to indicate the coordinate. And okay, the next one, the other points that I'm going to take because I extrapolate. Okay, so I'm going to take this point. And then I am going to draw using the ruler to draw so that I can draw my triangle. Make sure that you draw the triangle clearly so that the examiner knows that the triangle is large enough and the value of the gradient that you calculated will be more accurate. Okay, so this is the point. Okay, this is my point. Okay, right here. And then I'm going to join with that later, don't worry. And then horizontally. Oops, okay, screw up a bit. So this is the x-axis. I'm going to read that x coordinate from here. Okay, I am done. Oh yeah, okay, I need to draw the triangle. So I'm going to draw the triangle now, start from here. So this is the triangle that I used to calculate the gradient. Could you see that? And if you don't want to draw this big, it doesn't matter, right? The minimum size of your triangle must be at least occupying half of the length of your best fit line, right? So this is 15.2, right? 15.2 right here. X-axis is 15.2. And this is 51, 52, 53. 15.2 and 53. And 53. So this is how I calculate my gradient. So G is equal to 53 minus 3. 53 minus 3 divided by 15.2 minus 1.4. 15.2 minus 1.4. Let me do it. 53 minus 3, 50 divided by 15.2 minus 1.4, and, oh, sorry, 50 divided by 15.2 minus 1.4, and the value that I got was 3.62. Okay, this is 3.62. There's no unit for gradient. If you want to put a unit, make sure that you put it correctly. So in part 1, the internal diameter d of a cylinder is given by the equation d is equal to k square root of the gradient, where the k value is 1.13 cm. Calculate d for the test tube. Okay, d is equal to k 1.13 square root of your gradient, 3.62. So square root of my gradient times 1.13, and the value that I got was 2.15, right? Okay, 2.15. I put it in terms of three significant figures. Do you know why? Because see this word calculation. You see the word calculate, that means you have to follow the significant figures of the data, of the values, of the readings that you use to calculate. 1.13, three significant figures. 3.62, three significant figures. Three significant figures, right? So I'm going to put it as 2.15 cm. So 2.15 cm. So 2.1, okay. So the range of the d value is between 2.3. 2.1 minus 0.2 is from 1.9. This is a range, 1.9 cm to 2.3 cm. And of course, you can round it off to two significant figures, not a problem. Yeah. And the second part suggests one reason why your calculated value of D is only approximate. I want you to, okay, I'm going to scroll up and I want you to look at all the points, all the readings. Are all the points, all the readings are on the straight line? No, this is just a best fit line. The best fit line means that, okay, the points, the readings are close to it, but not all the readings are on the best fit line. So that is why I say the best fit line that I drew was just an approximate. Line of best fit is just an approximate line. So because not all the points are on this best fit line. Yeah, so I'm going to write that down. Line of best fit is an approximate line, as not all readings, okay, or not all the points are on the best fit line. That's the answer. Now, number 2A, a student investigates the light-dependent resistor, LDR. A student assembles a series circuit consisting of a power supply, a switch, a 470 ohm resistor, and an LDR. Fig 2.1 shows part of the circuit that the student assembles. Complete the circuit by adding the correct symbol for an LDR, light-dependent resistor, between Y and Z. Choose from the list provided in Fig 2.2. So which one is the correct one, right? Okay, light dependent resistor. So it depends on light. So you draw a resistor like this, and the light must hit on it. The arrows represents the ray of light that hitting on it, right? That is called LDR. Now, B part 1, the student closes a switch, connects a voltmeter across the 470 ohm resistor, records the reading on the voltmeter, opens the switch. On Fig 2.1, draw a voltmeter connected to measure the potential difference, or the PD, across the 470 ohm resistor. Where is 470 ohm? So you just draw. This is your voltmeter connected, okay? 2 points here. Just to measure the PD across it. And we are done with that. Now the second part, the voltmeter reading is shown in Fig 2.3. record the voltmeter reading VXY. If you want things to be easier for you, first step is to identify the smaller scale on this analog voltmeter. So you take 1 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1 divided by 10, don't you think you get 0.1? Yeah, 1 divided by 10, that is 0.1 volt. And before that, okay, I need to tell you that since this is a voltmeter, it is an apparatus. If you're using apparatus to do your measurement, just record your readings, yeah, by following the decimal points of the smaller scale on that apparatus. Voltmeter, smaller scale is 0.1 volt. So this is 0.5, 0.1, 0.2, 0.3, 0.4. This is 0.5, 0.6, 0.7, and 0.8. So I'm going to put here as 0.8 volt. Done. See, the current I in the circuit is calculated using the equation I is equal to Vxy divided by R, where R is 470 ohm. Use your voltmeter reading in B2 to calculate I. So all you need to do is just to sub in value 0.8 divided by 470 ohm. I must be measured in ampere, and the I value that I got was 0.0017 ampere. Right, so because voltmeter reading Vxy, this is calculation, yeah? Vxy has one significant figure. Calculation, you just look at the significant figures. Vxy has one significant figure, and 470, you can put 2 or 3 significant figures. That is why I put my I as 2 significant figures, 0.0017, and remember the unit, it is in ampere. Current must be measured in ampere. Now, the student, closes the switch, connects the voltmeter between points Y and Z, records the voltmeter readings, VYZ, opens the switch, and VYZ is given. Calculate the resistance RB. So I'm going to put RB is equal to 2.2 divided by I value that we calculated just now, 0.0017. So I got 1290 ohm. Wow, it is quite big. Right, or you want to round it off to 1300, it's not a problem. I'm going to put it in 3 significant figures, 1290 ohm. And the next one, E part 1, the student covers the LDR with a piece of card and repeats the procedure described in B and D. So you got VXY and VYZ. Calculate the resistance RD. In the dark using the equation 470 times VYZ, that is 2.9, divided by VXY, that is 0.15. And I got, wow, that is a very high value, 9090 ohm. Or you want to put it as 2 significant figures, 9100, not a problem. So I put 9090 ohm. Now, second part, the student removes the card from the top of the LDR and slowly leaves it vertically upwards, going up, away from the LDR until the card is 30 cm above the LDR. The student observes and records the readings on the voltmeter across the LDR VYZ as the card is raised. And this is table 2.1, shows the student's result. Describe how the PD across LDR or VYZ changes as the distance between the cord and the LDR increases. I want you to see this, right? From 0 to 5 to 10 to 15, we could see that the potential difference is decreasing. But from 20 onwards to 30, I would see that the potential difference, right, VYZ is constant. That is what I'm going to describe, right? Total resistance, okay, or I will say the potential difference from, okay, potential difference decreases. Potential, or just write PD because the question mentioned PD. PD across LDR. PD across LDR, okay, decreases from distance 0 cm to 15 cm. And then after that, the PD across LDR is constant. I want to see the word constant. From distance 20 cm to 30 cm. That's it. Now, when the LDR is covered by the card, the current in the circuit changes. Use the student's result from B part 2, D, okay, and E part 1 to show how this change in the current affects the value of the potential difference. Vxy plus Vyz. Okay, B part 2. Okay, I want you to see B part 2. Where is B part 2? You see Vxy is equal to 0.8. And then Vyz is equal to 2.2, right? And then E part 1, you could see that Vyz and Vxy are given both. So I'm going to find the total V. You know why? Because potential difference across the 470 ohm resistor and the potential difference across X, Y, and YZ are connected in series. So because the resistor and the LDR are connected in series, so the total potential difference represents Vxy plus Vyz. So I'm going to find the total potential difference of the circuit first. I'm going to write it here. Total PD of circuit. Right, okay. From B to N, okay, B part 2 and D, yeah? You could see that B part 2, okay, 0.8, and then D, Vxy is 0.8, okay. Vxy is 0.8 volt, Vyz is equal to 2.2 volt. And for E, part 1, you could see that given here. Vxy is 0.15 volt, Vyz is 2.9 volt. Okay, I'm going to write down. Vxy is 0.15 volt, Vyz is equal to 1.9 volt. So V total is equal to Vxy plus Vyz. So for B part 2 and D, you could see that 0.8 plus 2.2 volt, that is equal to 3.0 volt. For E part 1, V total is equal to Vxy plus Vyz. So 0.15 volt plus 1.9 volt. So you get 3.05 volt. I round it off to 3.1 volt. Could you see the difference is quite small? Since the difference is quite small, I would say that, okay, it does not affect that much because the total potential difference is constant. Yeah, the value of the potential difference is constant. Right, the total potential difference is constant. Right, so I'm going to write down first the answer. The total potential difference, okay, for B part 2 and D is equal to 2.2 volt plus 0.8 volt, which is equal to 3.0 volt. Total potential difference for E part 1 is equal to 0.15 volt plus 1.9 volt, which is equal to 3.05 volt, round it off, approximately 3.1 volt. The difference okay, sorry. Is 1 volt, right? Which is quite small. Hence, the value of total potential difference is approximately constant or constant. And we are done. Number 3, a student investigates the image formed by a converging lens. Refer to Fig 3.1. A, the student switches on the lamp, places the screen a distance d, which is equal to 80 cm, from an illuminated object, a triangular hole, in a piece of card, places the lens close to the illuminated object, moves the lens away from the illuminated object until a magnified, inverted, sharp image of the illuminated object is formed on the screen. Fig 3.1 shows the position of the lens when the image is sharp. First part, on Fig 3.1, measure to the nearest 0.1 cm the object distance x from the center of the lens to the illuminated object. All you need to do is just to place the ruler right between the two arrows of x. And the value that I got was 4.1 cm. And the second part, Fig 3.1 is drawn to scale of 1/5, 1 over 5, full size. Calculate the actual object distance x. So 1 over 5, object distance x is equal to 4.1 cm. I want x is equal to 4.1 times of 5. And I got 20.5 cm. So 20.5 cm is my answer. B, the student continues to move the lens away from the illuminated object until a second sharp image, which is diminished and inverted, is formed on the screen. Measures to the nearest 0.1 cm the object distance y from the center of the lens to the illuminated object, and y is given as 59.8 cm. Now, the first part, on Fig 3.2, shows the illuminated object. On Fig 3.2, draw a diminished inverted image in the space provided. So diminished is getting smaller, so you just draw a small one. And we are done. The second part, calculate the value d is equal to y minus x. The value of y is equal to 59.8 cm. Minus the x, 20.5. Remember, just now we just calculated. And I got 39.3 cm. So 39.3 cm is the answer. C, the focal length f of the lens can be found using the equation f is equal to capital D square minus a small d square divided by 4 times the capital D, where the value of capital D from A and D from B. Part 2, to calculate a value f1 for the focal length of the lens. Give your answer to 3 significant figures only. So f is equal to d square. From A, d square, big D. From A, the big D. Okay, which is 80 cm. Okay, 80, you just square it, minus the small little d here, 39.3 square, divided by 4 times 80. This is F1, and my F1 value, if I round it off to 3 significant figures, 15.2. 15.2 cm. So 15.2 cm. And then D, the student repeats the procedure in A and B for an object to screen distance D is equal to 100 cm. The student records the values of X, Y, and D. You get all the value. Calculate the second value of F2. So F2 is still the same. D square minus D square divided by 4D. So F2, the big, okay, capital D is 100 square minus 63.7 square divided by 4 times 100. And F2, I round it off to 3 significant figures and I got 14.9 cm. So 14.9 cm is my answer. E, the two quantities can be considered to be equal within the limit of experimental accuracy if the values are within 10% of each other. State whether your values of F1 and F2 from C and D can be considered equal. Support your statement with a calculation. So if there are two values of F and you want to calculate its percentage uncertainty, right? How do you do it? So you calculate percentage uncertainty of F. This is called percentage uncertainty. How uncertain? What is the error, right? So you get a bigger F, right? This is in this case, okay, larger, yeah? Bigger or larger F minus a smaller F divided by, you can choose. If you want to divide by a smaller value of F, it's up to you. Or if you want to divide by a larger of F, value of F, is up to you, right? So I'm going to divide with a smaller value of F. You can choose a larger value, not a problem, and times 100%. So percentage of F, I take 15.2 minus 14.9, I divide by the smaller value. 14.9 times 100%. And the percentage uncertainty, we call it. Percentage uncertainty of F is equal to 1.99% or 2%, right? So which is way smaller than 10%, right? So my statement is yes, right? The percentage, I write down percentage uncertainty of a value of F1 and F2 is equal to 1.99%, which is smaller than 10%. Right? So I would say that they can be considered equal. Now, F part 1, state one technique to use when doing this type of experiment to ensure that the image on the screen is focused as clearly as possible. You want to focus as clear as possible. You need to be patient, right? So you have to move the screen very slowly, right? Backward and forward until you identify the sharpest image. Right, so one technique, okay, move screen backward and forward slowly, yeah, until the sharpest image is determined. Now, the second part, the experiment is usually done in a darkened room. So explain how this makes it easier to see when the image is in focus. Because when the room is dark, the only light ray is from the illuminated object. So it will give you better contrast. So you know that, oh, bright means bright, dark means dark. So you could see the image form, right? Because due to the condition of the room, the dark room, you can see the image focus is quite clear. This is very different from when you conduct the experiment with full of lights in the lab. You could see that it's just one dot or the shape of it. It is clear but unclear in a way. So sometimes you are uncertain. Is this the sharpest image? But in the dark room, you can see it. When it get blur, you know right away due to a large contrast. Okay? Large contrast. Not constant. So sorry. Contrast. Okay. Contrast. And, okay, image, okay, can be seen very clearly. So you can determine the focus, the sharpest image easily. Right, number 4, wow, the last part. Hot water is poured into a glass beaker and allowed to cool down for 5 minutes. Plan an experiment to investigate whether the rate of cooling of the hot water depends upon the initial temperature of the hot water. The rate of cooling of the hot water can be calculated using the equation rate of cooling is equal to decrease in temperature divided by time taken. You are provided with first one, a supply of cold water, an electric kettle, a 250 cm cube glass beaker, a measuring cylinder. You may use any other common laboratory apparatus, and in your plan, include before that, I will skip that first. I will read the last part here. You may include a labeled diagram. That is what I want to show you. I included a labeled diagram. Right, so this is my labeled diagram. Right, I haven't labeled it, so I'm gonna label it. This is called thermometer. Right, because I will need to measure the temperature. This is stirrer. We have stirrer. Right, to make sure that the heat distributed evenly. Right, and then this is a beaker. This is hot water. And I am done with my diagram. So now my plan, I am going to include any other apparatus needed here. So I need, because they are just providing, they didn't provide me with thermometer. I need a thermometer, and I need to, rate of cooling need the time taken. So I need a stopwatch, right? Additional apparatus, okay. Or I write here, additional apparatus. That would be my measuring cylinder. Measuring cylinder is given thermometer. I need a thermometer. Thermometer and a stopwatch. And I'm done with the first part. Second, a brief description of the method, including what you measure and how you will make sure your measurements are accurate, remember. So this is my methods. So since I draw a diagram, I say set up apparatus as shown in the diagram. And the second part, maybe, okay, water of how much water is given? 250. So I only need 200. 200 cm cube is measured by measuring cylinder. And then third, water is heated by electric kettle to 100 degrees Celsius until it boils, and then and pour into beaker. Done. And then initial temperature of the water. Temperature of water is measured by thermometer. Okay, and then after 5 minutes, I say I would take the final temperature of water, right? So because maybe okay, after 5 minutes, final temperature of water is taken. Experiment, because they ask us to explain. Could you see right here? You have to, how do you make sure that your variables, how are you going to make sure that your measurements are accurate? So experiment is repeated and average. And then number 6, I would say that last part, I would say repeat. Remember, last part of the method, always repeat. Experiment is repeated with initial, because different initial temperature. Temperature of hot water. You may suggest of 90 degrees Celsius. Maybe you start with 80 degrees Celsius, 60 degrees Celsius, and 50 degrees Celsius. And then stirrer, okay, is used to make sure heat distributed evenly in, okay, beaker. We are done with that, right? Because after all, remember, this student is going to investigate whether rate of cooling cool down for 5 minutes, remember. So the time is actually constant. Right now, the variables you will control, okay? So I'm going to write controlled variable right here. Controlled variables. This is plurals. Maybe I will say volume of the water, volume of water, and surroundings, temperature, time of cooling, 5 minutes, remember? Right? It is enough for you to write more than one. Done with that. And the next one, a results table to record your measurements. You are not required to enter any readings in the table. So you don't enter any reading. So this is my table. So my table looks like this. Initial temperature of water, degrees Celsius, and then just put like this. And then final temperature, I write it smaller, temperature of water, degrees Celsius, and then decrease in temperature after 5 minutes, okay? Decrease in temperature. Okay, still in degrees Celsius, and then this is rate of cooling. Rate of cooling. Rate of cooling is degrees Celsius per time taken. Now, okay, use a ruler, right? Draw nicely, at least, okay, nicer. Split this. So we are not supposed to enter any reading, so you just leave a blank table like that. That will do. And then we are reaching the last part. Okay, whenever I finish writing about that part, I will make a tick so that it's easier for me to see how many parts, okay? How many more that I need to write. And the last part, how you will process your results to reach a conclusion. So since I have all the values right here, so the conclusion, okay, I will say plot a graph of initial temperature of water against rate of cooling to see the relationship, because you cannot give the result. You are just a planner. Right, so that is the end of it. So nice work reaching the end, physics legends. Now you know exactly how to tackle those tricky paper 6 questions like a pro. If you learn something new, smash that like button and hit subscribe, because I've got more papers and physics, right, coming your way. So till next time, stay curious, stay confident, and keep mastering physics with Tanya Chew. Bye.